All right, so I wanted to talk about a couple things about radioactivity. The first thing is the half-life. The half-life is the time required for some amount of radioactive material to decrease by one half. All right, so you start out with something that's radioactive, and then it turns into something else, and that process takes a certain amount of time. So you're waiting for half of the atoms to turn into something else. So let's take a look here at what we're talking about when we say something's unstable. Here's a stable carbon 12 atom. The mass number is 12. If I add some neutrons, now the nucleus becomes unstable. And because of that, it wants to do something to become stable. Think of this as popcorn, right? Popcorn as a kernel can be unstable to become the more stable, fluffy thing that you eat at movies. So this is sort of like the nucleus when it's on edge, and this is sort of the nucleus when it becomes stable after it does something radioactive. And the half-life is the amount of time it takes for half of the popcorn to convert to the more stable, edible, fluffy treat. All right, so that's what half-life talks about. So in a certain half-life, you would lose from 1,000 atoms, 500 would be lost in the first half-life. Then the second half-life would lose another half, so half of 500 is 250. Then another half-life would lose half of the 250, which is 125, and so forth. So another way to think about this, if you're familiar with the Marvel stuff, Thanos does his snap and half of the world dies, right? If he snapped again, it's not that the other half of the world would die, it would be half of everything that was left. So if he can take away half of the world with one snap, his second snap would take away half of what was left. His next snap would take away half of what was left. And that's what half-life is, real quick. So half-life is how carbon dating works. There's a little bit of radioactive carbon, like I just showed you, C14, in everything we eat. And so you're replenishing your body with a little bit of radioactivity. That radioactivity percentage is going to remain constant until the day you die, or in this case, the fish dies. And then you won't be replenishing it anymore. So de, um, it'll undergo radioactive decay and disappear. And based on what we just saw here, so in a certain amount of time, there'd be 500 left. In a certain amount of time, there'd be 250 left. And so every one of these jumps we know because that's a constant. So for carbon 14, it's 5,730 years for half of the carbon to disappear. So as you can see here, there are different times for different elements. You won't need to know that. But the next thing I wanted to talk about is Marie Curie. Her and her husband Pierre sort of came upon radioactive decay in 1898, which, if you're keeping score, was right before um, Thompson. No, right before Rutherford and right after Thomson. So just like Thomson did, she did this experiment where she put radioactivity in there. She wanted to see if there was positive or negative things. If it was tilting toward the positive, then it would be a negative thing. If it tilted toward the negative, it would be a positive thing. Remember when J.J. Thomson did this, everything went up. And so he found that there were electrons. So what she found is in radioactivity, it actually went all three places. So there was some that went up, there was some that went straight, and there's some that went down. So that means the alpha rays have a positive charge, the gamma rays are neutral, and the beta rays have a negative charge. So that's what she sort of figured out. And then, with a little more investigation, she determined that the alpha radiation, the stuff that went down with the positive charge, was a helium nucleus. So that has very low penetrating power, has that positive charge. The beta radiation, the stuff that went up and had a negative charge, turns out that was just an electron, just like Thomson figured out. That has medium penetration. We'll talk about that in a second. And then the stuff that just went straight is gamma radiation, has very high penetrating power and has no charge. So here's a nice example of what happens here. Alpha particles can't even penetrate paper. They're only hazardous to humans if you get them in your mouth somehow and it gets into your body that way, if you like inhale it or eat it or something. Beta particles can go through paper, can go through flesh and bounce off of metal. So beta particles can get into things, can penetrate things more than alpha. Neutrons can get all the way through metal as well and stop at water and gamma radiation, thing that makes hulks, right? So we can make a little hulk, make a hulk smash. There you go. So just to bring that, to full, we got to make sure. All right, so there's Hulk, and that's what happens with gamma. He's got some long legs. Anyway, all right. So last thing I wanted to teach you is how radioactivity works. And basically, what you need to do when you're doing these radioactivity problems is recognize that the arrow is an equal sign, and everything on one side of the arrow has to equal everything on the other side of the arrow. So what we have here is 238 on one side of the arrow, and on the other side, 234 and 4. And 238 equals 234, thanks dyslexia, and 4, right? 234 plus 4 equals 238. And then on the bottom side, we got the same situation going. All right, 92 equals 90 plus 2. So it's a nice way to determine what's missing. So this is the alpha decay, right? So the top thing's equal, the bottom thing's equal. And now we have an alpha particle after all that. All right, that helium nucleus. Here is that beta particle, right? And we do the tops, and the top ones are going to equal 14 equals at the arrow. So that's an equal sign. So 14 equals 14 plus 0. And on the bottom, we have 6 equals 7 minus 1. So there's your equals. So 6 equals 7 minus 1. And that's a beta particle. All right. So that's the kind of stuff I want you to be able to do for your work. So for this example here, we're trying to figure out what it makes. 238 equals 234 plus what? Right? 238 equals 234 plus 4. 234 plus 4 equals 238. So now we know whatever this is has a 4. And then on the bottom one, 94 equals 92 plus what? So this equals 92 plus what? So 94 equals 92 plus what? So that's going to be a 2. So what we have is something that has a mass of 4 and a protons of 2. And if you go to your periodic table, you will see that is helium, right? So that's an alpha particle that was released. So we can really quickly look at our periodic table and find out that that's helium right there, 2 protons. All right. So this is a kind of, another fun thing to do. It's fun. So here, if we're trying to figure out these numbers that are missing, we know that the top numbers equal each other after the arrow. So 210 equals question mark plus 0. So therefore, that must be 210. So that's 210. And then in the bottom ones, question mark equals 83 minus 1, right? So question mark equals 83 minus 1. So that equals 82. So we learned that that number is an 82, and we learned that that number is a 210. And that's how you're going to do this for your homework. Um, some examples. Let me show you an example real quick. Should have had this ready. All right, so for this example here, the top numbers have to equal each other. So 42 equals, because there's the arrow, 42 equals 0 plus A. So if 42 equals 0 plus A has to be 42. And so when solving for A, it's 42. Here, we're looking at the bottom ones for B. 19 equals, there's your arrow, minus 1 plus B. So 19 equals 20 minus B, right? 20 minus 1 equals 19, and there's the equal sign. So that'll be 20. So therefore, this must be something that has 20 protons and a mass of 42. And if we go to the periodic table, 20 protons, that must be calcium because it has 20 protons right there. All right, so that's how you do that. Let me know if you have problems. Come see me during office hours.